The reason for being here in Amsterdam, having a meeting, is by SCORE, Scientific Committee on Oceanic Research, which works on plankton, foraminifera and ocean changes. So people from different countries of the whole world are here, from Taiwan, from South Africa, providing knowledge and ideas and also setting signs in the future for the young generation to come.
If we want to understand how the climate and the ecosystems are going to change in the future, we need to know what is the baseline variability, how the climate systems and the ecosystems in the ocean are reacting to change. And unfortunately, our historical records are simply too short. We need to look over time periods of hundreds, thousands, 10,000s to millions of years. And for that, we need some kind of a recorder of the conditions and events in the past. And this recorder, in our case planktonic foraminifera, doesn't have it written on themselves. What was the temperature of the ocean, what was the pH of the ocean, etc. It has clues, and we use this information as a proxy, an indirect way of reconstructing the past climate.
So live ones we can study alive, meaning what are they doing, how do they eat, what do they eat, how do they live, how do they generate their shells, and so on and so on. This is a process study. The dead ones are a wonderful archive on the seafloor, namely to study what happened through time and what can we get out of them in relation to what we know and more we get to know from the living ones. So it's a combination between the biological part and the geological part.
It's remarkable. If you look at the size of these tiny little animals, they are less than 0.5 millimeter. They are barely visible by naked eye. And yet, by an analysis of only a few shells of these organisms, you can tell the state of the global climate, how much ice was on land, locked in the ice sheets, what was the global temperature, what was the pH of the oceans, and thereby the CO2 concentration in the atmosphere.
Jumping in the water at 7 o'clock in the morning. It was a little bit difficult.
Sorry, I'm not in the mood to act right now.
I never get tired of this. The reason we study plankton is to get a firm understanding of how the base of the marine food chain operates. The plankton contain a very interesting archive of environmental information incorporated into organisms that grow. Shells such as foraminifera and pteropods and coccolithophorids allow us to reconstruct what the environment of the ocean was like in times past.
It's simply fascination. They are unicellular, single cells, and yet so complex. They can exhibit so many interesting behaviors, and they are enormously useful.
The primary mission of the last 30 years of culturing of these organisms is to develop the calibrations and the tools, the proxies, so to speak, that allow us to reconstruct ocean temperatures, salinity, pH, things like that, with a very high degree of confidence.
The reason we go to the Wrigley Marine Science Center is because it provides access to deep water, which is necessary if you want to work with planktonic foraminifera. Also, there's a fantastic infrastructure, and the abundance of the forams is high enough that you can go after them diving.
Organisms such as foraminifera are at the fingertips of divers, and they can collect these organisms just by looking in the water column up in the upper 1 or 2 meters and bring them back into the laboratory within a half hour.
We're one of the few groups that cultures foraminifera live in the laboratory, and we are part of the only group that collects them via scuba diving rather than with a plankton net. And so the condition of the forams when we get them is really excellent.
Well, when the forams are caught and you bring them back to the lab, what you do is you're going to expose them to the environmental parameter, be it temperature or pH or light or feeding, and then you maintain them in seawater that may be modified as well, and then you keep them alive, you keep them happy.
So here we're growing Foraminifera, and we're culturing them under controlled conditions in ways that's hard to do in specimens that you would just collect from the ocean. And that allows us to understand how they respond to different environmental conditions, different experimental conditions, and find out what are the basic chemical mechanisms that control how they grow their skeletons.
That's a falcon flask, and it's different from the typical culture jars because the forams that don't have spines, they sink to the bottom, and they attach themselves right here to the bottom, and then we can use this to view them and take pictures and sort of assess their health.
Okay, so we've just fed an Orbulina universe and Artemia, and it bumped into the spines.
They're ferocious. They grab those nuclei and pull them apart, you know. You want them to grow. You want them to produce calcium carbonate that contains isotopes that you're looking after. So you need to feed them. And we feed them at rates that are normal in the ocean. We feed them the food that they normally eat in the ocean, copepods, Artemias.
I suspect that feeding Artemia to Foraminifera is equivalent of feeding potato chips to a human being. I think there's a lot of fat and lipid in this guy, but I just have to keep the Foraminifera alive for 2 or 3 days. The shell will fully calcify, and we'll have Orbulina sitting in our micropaleo slides ready for geochemical analysis. It's really interesting that the Foraminifera record itself goes back more than 100 million years, back to the age of the dinosaurs. And the work that we're doing today, working on living Foraminifera, all right, is allowing us to develop a suite of tools that has the ability to reconstruct the environmental conditions in the oceans going back tens, 20, 30, 40, maybe even 100 million years.
My specific quest is to understand the carbonate chemistry in Earth history. I want to know what the carbon perturbation that we are causing today is going to do with the environment, what it means for society. And to do that, you first need to reconstruct what it did in the past.
I think one of the most important components of the culturing project is that we are moving from this approximation term to actually calibrating the geochemical tools so even though they're called proxies, they are about as close as you can get to having an instrumental measurement of what was going on in times past without having these really tight calibrations. It wouldn't be possible for us to have a lot of confidence on the temperature or pH or salinity conditions that existed in the past.
There's several ways to develop these calibration relationships. One is to go out and do plankton tows and collect living creatures from the ocean and analyze their shells and measure the ocean conditions where you are. And you can also take shells from sediment cores, the top of it, the modern stuff, and measure the composition of the shell and the composition of the seawater and develop the relationship. But the problem with that is that there are so many other variables. Usually when temperature is different, pH is also different, salinity is different, the nutrient content's different. And in culture programs like this one, you control all those variables. So only the one that you think is responsible, or the one you want to test, is varying.
As you develop new techniques, you come up with new relationships between the chemistry of the shells and the environment. But one of the main challenges is also to get a higher accuracy and precision, so the reconstruction become more accurate.
Using some of these new analytical techniques and discovering for the first time that we're able to see variation within the shell that shows some kind of biological control. The Foraminifera that we work on have just a single cell, just one cell, and they're able to exert this tremendous control on the chemistry of their shell. And they're also able to record very rapid changes in ocean chemistry and in conditions over really short time scales. And so that's really cool.
Like when you're back home doing the analysis in a different kind of lab by yourself, you get a little stale. And so when you go to a conference or when you spend a lot of time with people like we are here, it's just completely renovating or invigorating. Yeah.
And then they're just beautiful. I mean, you can see them under the microscope. I work with forams and I also work with coral, and I just feel lucky to be able to go to work and interact with these beautiful creatures. I mean, you can see it around the lab sometimes when people see something that they're excited about. They'll shout out, I mean, because they're just fun to work with too.
Do you see what I'm talking about? How there's like a splat of rhizopodia and then really long. They almost look like spines, but they're not.
Jen is making observations on Neogloboquadrina dudatri. It's got symbionts, and I think that the plankton toe material working with the non-spinos is going to open up new vistas in what we learn about this particular group of Foraminifera. Nobody's ever looked at it before. Based on the discoveries that we've made over the last 10 or 15 years, which effectively has been about every 3 or 4 years we make a major discovery out here on how Foraminifera tick and how we can better reconstruct environmental conditions in the fossil record. I think there are still some really good questions out there that need to be answered, and I think that the elemental composition of Foraminifera is going to play a very prominent role in those future discoveries that are being made.
What we are realizing right now is that we have enormous multitude of methods and instruments to measure every isotope and trace element in the foraminiferal shells that you can imagine. But we're realizing that we know not as much as we need about the ecology and the physiology of these organisms. Where exactly do they calcify in the water column? What is controlling this position and the time of the calcification? How do they incorporate all these elements into their calcite? And we are increasingly realizing that it's more a biological perspective on foraminifera that we need to understand.
I don't think there will be an end to this, because basically you go from a very optimistic proxy, this is great, and then you find the downsides, and so you're working on the downsides, you're trying to solve several issues. At the end, what you want to do is to have a mechanistic understanding of how a environmental parameter is reflected in the geochemistry of a proxy.
Ocean atmosphere interactions, which is very big scale, over broad, long time periods. That's very big scale thinking. You're focusing in on, using microscopes and focusing in at the micron level. And that's fascinating to me. I mean, it's just very exciting.
Yes! Yes! Look at this. This is amazing. I am so lucky to be able to work here. I get to be outdoors a lot. I get to travel and meet really interesting people.
We're just sort of carrying the torch and training the next generation of planktonic foram hunters. The graduate students have this opportunity to really make a difference, work on a project that has that fundamental science and research foundation that they know their research could move a field forward.
And this is challenging in this job. You get new, curious people who sometimes ask questions which you never dared asking yourself. And this is a challenge for us.
Everybody is part of the team. And the way you generate new ideas is by discussions.
Students change when they spend a month out here in the field with us.
Watch out there. Okay. I've never seen so many dolphins or forams.